Hello, this is Philip Seagraves with Georgia State University. We are going to do an express tour of some special issues with multiple regression. Keep in mind this is not intended to be a deep dive on these topics, just designed to introduce you to the concepts and give you some thoughts about maybe where to search for more information or when to bring in the heavy guns and invite somebody that is a stats guru to help you deal with some of these issues. We're going to deal with four things primarily. And the first of those is dealing with categorical variables and converting those into dummies. And the next is to identify and eliminate multicollinearity. Third, using interaction terms and what are they all about. And also a topic called heteroscedasticity. The first of those topics is dummy variables. Often our data will arrive in the form of words, things like red, black, blue. And it could be something as simple as yes, no on a column that has a feature. Like if you're looking at real estate data, you might have homes that have a pool, and it may say yes or no. But we have to deal with that mathematically in a regression model. So how are we going to do that? Well, the first temptation with this data, particularly with these colors, for example, we may try to code those, just 1, 2, or 3, and just use a value, and then let the regression work with that. Well, that could be coded a number of different ways depending on who's dealing with the data. We could have red as a 1, 2 as black, and 3 as blue. But we could also have red as 3, black as 1, and 2 as blue. Well, when we run the results using this first original coding, we'll see that we have an adjusted R squared of 0.64, a coefficient on color of -5. What is that? -5 what? The color, if a color is 2, we give it a -10. The color is 3, we give a -15. Just doesn't seem to make a whole lot of sense, particularly if you consider that we could have coded it another way. And we just arbitrarily assign those values to the colors. Now, color is a 6.66. If color is 1, we have a value of 6.6. If color is 2, we double that value. And you can see that observation number 10 on our predicted value is different in either case. We have a 79.8 on the second type of coding, and if we go back, we have a 78.172 on our original coding. So what does that mean we should do? Well, the proper way to code dummy variables is to use one less column then you have total options for that dummy variable. In this one we have 3 options, red, black, and blue. So we would use 2 separate dummy columns. And we just leave one of them out. In the first example here we've left out the blue. So if you have red, there's a 1 in the red column. If you have black, there's a 1 in the black column. If you have zeros in both columns, it has to be what color? Well, blue, of course. Let's look at another way of doing it. In this one we've left out red. So we have a 0 in both columns if it's red, a 1 in black if it's black, and a 1 in the blue column if it's blue. So you can see that this is the same record. This is a blue car, and you can see this is a red car. It's got a 1 in the red, and over here it's got zeros in both, which indicates that it's a red. Well, what if we run these regressions for the original values? What are we going to come up with? It looks like this is an insurance example looking at how many accidents per 10,000 cars. It looks like that if you have a red car, you have 10 accidents. But this is not really the correct interpretation because the intercept includes the number of accidents for blue cars, the case that's not included, that we don't have a dummy for. So the interpretation on this dummy variable is what the difference is between blue and red. So we find that the intercept is 138.8, and that's with a blue car. For red cars, we expect 10 more accidents. For black cars, compared to blue, we expect 3.3 fewer accidents. So in observation number 10, we predict 80.95 accidents. Well, what about coding it the other way? Well, now we've left out red. So compared to red cars, black have 13.3 fewer accidents, and blues have 10 fewer accidents. Sounds like red is the sportiest car that has the most accidents. Could be the drivers that choose red cars, but who knows. And we see now that number 10 has the same predicted value. No matter which way we code the variables, as long as we're leaving one out, we're going to get the same predictions, the same r squared. We will get different coefficients, but they're essentially the same if you interpret them properly. Well, what about our next topic in dealing with regression? Multicollinearity. This refers to a situation where you've got multiple independent variables in your model that are nearly or perfectly linear related to each other. Let's think about our feet. If you've got a big left foot, you've probably got a big right foot. If you've got a big right foot, you've probably got a big left foot. Same thing for small feet. If we look at our data set here, nobody's feet are the exact same length, left and right, but they're pretty darn close. We also know that there should be a relationship between height and your feet. So there's a relationship between height and your right foot. There's also a relationship between your height and your left foot, and it's probably about the same relationship. Let's take a look at it with this sample set. We find that our right foot goes up an inch. Our height is about 4 inches higher. Same thing with our left. As our left foot size increases by an inch, our height increases by about 3.99. But note that the coefficients aren't exactly the same. We have 3.993 for the right foot, 3.995 for the left foot. Well, what happens when we run these two guys in the regression together? Well, our results are going to be the same for our model. In fact, the model might perform a little bit better, but look at these coefficients. Our right foot being 1 inch longer is related to height being 8.5 inches taller. But our left, if our left foot is 1 inch longer, our left foot is 1 inch longer, then our height is -4. We get shorter with a longer left foot. That doesn't make sense at all. And the problem with this is if we take another sample where these coefficients are a little bit different in the other direction, we might get the exact opposite result on these coefficients for left and right. In this case, we would normally delete one of those values. And this can happen in other types of data as well. You might find in housing data that the number of bathrooms and the number of bedrooms are highly correlated. You might find that the size of the house is highly correlated with some other variables like that. Maybe even the size of the lot is correlated with the size of the house. If they are perfectly linear related, then you've got to exclude one of them or you'll get very unpredictable results and things just may not make sense. The next issue that we're dealing with, and the reason is because these variables, as I've said, are highly correlated. Left and right foot. The left and the right foot are 0.999, have a correlation of 0.99999. And we only need one of those values. The other foot doesn't add really any additional information. Well, what about interaction? We also find in many cases that not only can we increase the slope by having something like a pool or male or female may mean that you have a higher value on the intercept term in the equation in a regression. We also might find that variable like age, like gender, and maybe even a continuous variable might even impact the slope of the relationship. But what does that mean? Let's take a look at some data. We have observations here, and these are your reflexes, like when the doctor hits you in the knee, how far your leg kicks out. And we have the age, and we have gender. And we're just looking at the first 11 observations, but we have females are coded with a 0 and males are coded with a 1, and we have ages and our scores for reflexes. Well, how about our data? Here it is all together. We just have age and the reflex score, but we don't know who the males and females are. In this chart down here, we know who the males and females are. The pink is the females, and we have an intercept that's a little bit lower. And we also have a slope that's not quite as steep. In the males, we have the intercept value which is higher, but it falls off. As the males get older, their reflexes seem to fall off faster. Well, let's take a look at a regression with just this data up here, just the age and the reflex and the gender together with all those three together, and we find that unfortunately, because the gender is all mixed in, we don't have a significant relationship. We really don't have the relationship between gender and age modeled in here at all. Well, how do we do that? To model the interaction between two variables, we simply multiply those variables together. We multiply age times gender. Well, because gender takes a 1 and a 0 value, we'll see that with females, we end up with nothing in our age-gender interaction variable. But in the males, we end up with the same value we had in the age. We have it in there a second time, but it's only in there for the males. We don't have the ages in for the females. Well, what does that do with our regression? Let's take a look. Now we have an intercept of 90. We have a gender variable, which is now very significant, if you see. We have age, which is significant as it had been, and we have age and gender, this new term, which is significant. Well, take a look at these coefficients. We have 90 as an intercept, and remember, that's female. And then we have a 24, which is our gender dummy variable. Let's go back and take a look at our chart. We'll take a look at the approximate intercept for our females. There it is. It's about 90, and about 20 more than that, we have our intercept for our males. We'll take a look at the slopes. We have a slope here for the females and a little bit steeper slope downward for the males. And where is that? Well, take a look at here. We have our slope for our base, which is our females, of negative 0.51, and we have an addition to the slope, a minus 0.55, for males. So for males, as we get older, reflexes drop 0.558 more than females per year, and that's evidenced in that slope. You can see it's a little bit steeper for the males. So the way we interpret the meaning of the x1 and x2, they interact with each other if the impact of x1 on the y changes as the value of x2 changes. So that means that the slope essentially is changing as well based on the age. So in this example, age and reflexes is different for males and females. So they interact. Well, this is different from multicollinearity. Multicollinearity is when we have a relationship between two of our x variables, and they are perfectly related with each other, but they're not changing the value of the slope of the equation. And finally, we have an issue called heteroscedasticity. In this one, as our values increase, and this one we're really looking at at data over time, we see the water level going down, but over time it's getting much more variable. And if we try to make predictions about what's happened over this course of time, we're not going to be able to make predictions around the variability because it's not the same throughout our entire data set. We end up with the same thing on this chart. We're looking at the percentage of money spent on luxury goods as a function of income. As incomes rise, people certainly do spend more money on luxury goods, but the variability gets much greater. It kind of fans out. And this gives us less reliable predictions and forecasts because the variation changes. This is called heteroscedasticity. So we can see this in our results. We can also see this in residual plots of our data. And there are a number of different transformations that we can do, including logging our variables to make adjustments for this. And I'm probably not going to spend a lot more detail in the depth of this particular class on this topic, but just be aware that we can make transformations, but the type of transformation really depends on the data that you're dealing with. And this may be one of those cases where you're going to bring in the experts and maybe do a little bit more research on nonlinear transformations for dealing with issues like heteroscedasticity. Again, this is intended just to be a brief, quick overview of some of these concepts, give you some pictures and tell you how to identify some of these things, and at least point you in the right direction on where to turn to deal with issues such as dummy variables, interaction terms, heteroscedasticity. All right, and multicollinearity, of course. Hope you guys have had a great time listening to this presentation, and want to thank Dr. Satish Nargunkar for providing these slides and all of his mentoring. Thank you very much. Bye.